Good morning. So again, I'm just going to take a moment to thank a lot of collaborators, some of whom are on the call here. This was really a group effort, and so what I'm going to do is go a little bit deeper than Jenny's talk, and a little bit further into the subduction zone. And again, just to reiterate, Voila wanted to take a whole systems approach to really understand subduction zone processes, to look at, what's coming into the subduction zone, what's being released into the mantle wedge, and then try and link that to what is going on in the volcanic arc. And so we took a very interdisciplinary approach. And I'll apologize, I'll go quite quickly. So I think Jenny kind of set up rather nicely the motivation for trying to look at the Lesser Antilles to understand the differences, how the differences in the incoming plate manifest themselves in terms of structures that we image and understand in the Lesser Antilles arc, so that we can make comparisons globally to understand subduction zones in general. Uh, one of the one of the motivating factors that Jenny alluded to in her in the previous talk was trying to understand how these large offset fracture zones interact and produce fluids in the subduction zone system. And so the Lesser Antilles is one of these really interesting places, and one of the few places on Earth that we can look at slow spread oceanic lithosphere being subducted. And it's also important because it has several large offset fracture zones, so the 15, 20, the Marathon, the Mercurius, Vima, and Doldrums going into the system. And one of the hypotheses for the experiment was, are these places where there's deep hydration, and do we see evidence for this deep hydration coming out in the mantle wedge and in the volcanic arc? And it really is a global end member. It has an old slab going into the system. It's about 90 million years. It's going relatively slowly, so at about 2 centimeters per year. And there are also large changes in sediment along strike. And so we deployed 34 broadband ocean bottom seismometers, and this was in addition to the regional background seismic array. And this produced a really nice array geometry for us to do our imaging. And again, in addition, there were some really nice experiments by Jenny and Tim looking at the incoming plate so that we could really tightly constrain things. Um, and I think Jenny did a nice job of setting up. The short answer is the incoming plate is heterogeneous. So the fracture zones may not be doing exactly what we think they are, but we'll get into that. Here's just some pretty pictures. Most of the ocean bottom seismic work was done off the James Cook, and these are all from Steve actually, and some of the land deployment pictures. Terrible place to work. Wouldn't recommend it. And so today I'm going to focus more on, instead of what's going down, I'm going to focus on where fluids are coming off the slab, where melt and fluids are in the wedge, and can we relate these to what's going on in the volcanic arc outputs. So one of the important things we had to do was try to understand where those fracture zones might be after they've been subducted. So we developed a couple of different methods for tracking those fracture zones. So on the right-hand side, I'm just showing the surface projection of these fracture zones based on an estimate from G-Plate software. And then we developed a kinematic method where we basically just march those fracture zones down the slab through time. And then we developed another method, multi-dimensional scaling, which basically unfolds the slab to the surface and creates a map between the surface projection and the subsurface projection. And the end result of that is, between the two methods, the prediction for the fracture zone locations on the slab are plotted, and there's pretty good agreement. So we were pretty confident that we knew where those were. Okay, so I'm going to give you a whirlwind tour of the subsurface. I'm going to start with where we think fluids are coming off the slab, and then we'll look at where fluids might be in the mantle wedge, and then we'll try to get into where they're coming out of the arc. So this is some nice work by Lidong B. And we're looking at the VPVS anomaly from the local tomography. So just to orient you, this is Guadeloupe here. It looks like a butterfly. Martinique down here looks like a mitten. And Dominica's in between. There are several high VPVS anomalies. And again, ripping off of Jenny's talk earlier, high VPVS would be regions that we think are hydrated, either serpentinized material or actually have partial melt or fluids associated with them. So what we're looking at here is a slice along the top of the slab. So these are just showing you slab depth contours. And there are three highlighted anomalies. A is likely related to sediments and a deeper subduction channel in the north. But then B and C, we think, are actually related to slab alteration near the fracture zone. So, but again, what we don't see is that the fracture zones light up as a single continuous high VPVS anomaly. What we see is that there seems to be heterogeneity, and there are other places that might also have high VPVS ratios. But these two, B and C, seem to line up nicely with the Marathon and Mercurius fracture zones. So we can also look at this with attenuation, and this is some nice work by Steve Hicks. So on the left-hand panel, I'm showing you, so attenuation is the energy lost per cycle of a seismic wave. So it's the reduction in amplitude as the wave propagates through, and that gives us information about how energy is being lost either through intrinsic attenuation, so grain boundary sliding or other mechanisms, or if there's some other scattering effect that we're not accounting for. And so on the left-hand side, I'm showing you the shear Q anomaly or shear attenuation anomaly. And on the right-hand side, I'm showing the bulk attenuation to shear attenuation anomaly. So, and what's shown here along the gray line is the top of the slab. And there's a very high shear attenuation anomaly in the mantle wedge, which I'll talk about later. But if we look at the area just above the slab, just above, we see that there's not a very strong shear attenuation anomaly. So it looks like it's pretty cold. Usually lower temperature things have less attenuation. So the top of the slab looks pretty cold according to the shear attenuation. But then if we look at the bulk to shear attenuation, there seems to be a rather high ratio. And typically we think bulk to shear attenuation should kind of track VPVS. It shouldn't really break above, around 2, but it goes to rather high values here. And what's plotted along the top of the slab here, this is the VPVS anomaly. So there's a high VPVS anomaly and a high uh, bulk attenuation to shear attenuation. And Steve very cleverly came up with the interpretation. Well, this might be an indication that there are free fluids just above the slab, and it's not partial melt because the shear attenuation is telling us that it's a relatively cold temperature above the slab, but the VPVS anomaly and the bulk to shear attenuation are telling us that there may be free fluids, and the high attenuation ratio anomaly is probably caused by some sort of scattering effect rather than intrinsic attenuation. And the interpretation of this is that there are fluids being dragged down by the plate in a 40-kilometer thick cold channel just above the slab, which is interesting. And it's telling us that, the grand scheme of things, we typically think that, fluids are released from the slab. They rocket their way up vertically straight towards the surface, towards the base of the crust where they cause melting and the melt comes up. But what this is telling us is that there may be a more complex fluid pathway. Okay, so we can look at shear velocity, and low shear velocities in the mantle are typically associated with the presence of partial melt, or in this case, also potentially free fluids, because fluids have a zero shear velocity. When you average them together, they tend to reduce the shear velocity significantly. And in general, so we have absolute velocity here that ranges from 4.1 to 4.6. Typically, for mantle rocks, it's really difficult to have a solid peridotite that has a velocity of less than 4.2 kilometers per second. So these red regions are really highlighting regions where we think there might be partial melt. Okay, so these are what we're looking at in these panels are just depth slices at 40 through 125 kilometers. And the salient features are this very fast blue region, that's the slab coming in, it's tabular. At this depth at 100 kilometers, the slab shows up really nicely. So that's our subducting slab. The interesting thing is, it may be hard to see on small screens, but the islands are plotted here. And beneath the volcanic arc in general, we see there are some anomalies, not beneath all islands, but particularly beneath Martinique and Dominica, there's a particularly strong anomaly, but there are smaller ones beneath St. Vincent and also Montserrat, which have actively erupted in the recent past. But it's also interesting to note that the low velocity anomalies aren't just centered beneath the arc, but they actually extend a couple hundred kilometers into the back arc. So again, this is suggesting that we don't just have vertical ascent of melt, but actually there may be significant melting in the back arc. And again, we can look at this in profile view. So I like to joke, this is my first subduction zone model here. There's a nice subducting slab. And we can see that beneath the volcanic arc, which is these peaks here that are in the bathymetry that are sticking above water, we do see there's a low velocity anomaly in the mantle, but we can also see in the back arc here beneath the lithosphere, so there's a rather thick lithosphere, about 60 to 70 kilometers thick. There is a low velocity anomaly that seems to be present, particularly in the back arc, but behind Dominica. So again, suggesting something is pooling or ponding melt in the back arc, and that's being fed back towards the arc. Okay, and it's not just the shear velocity model from surface waves. We also see this in the attenuation model. So the arc is visible, but we also see a rather deep and strong attenuation anomaly that extends into the back arc as far as our resolution can see, but it's not centered directly beneath the arc. And it's not consistent from north to south either. It's focused behind Guadeloupe, Dominica, and Martinique. Okay, and then again, we can look at this in another way. We can look at S to P receiver functions, which give us an idea of both crustal structure along arc and also where the lithosphere-asthenosphere boundary might be. We typically don't think we should see a lithosphere-asthenosphere boundary given a simple thermal model, but in order to sharpen that up, we can have partial melt ponding at the base of the lithosphere, and that can help make a lithosphere-asthenosphere boundary apparent in a receiver function image. So what we're looking at here from A to A prime, A to A prime in the north, as a transect along the arc, and this red phase is a velocity increase with depth, which is the moho. And then in the northern part of the section, we see evidence for a velocity decrease with depth, which would be consistent with the lithosphere-asthenosphere boundary. But it's not as visible in the south, suggesting that there may be more melt ponding in the north, again, consistent with what we showed earlier with the surface wave imaging and also with the attenuation anomaly, that there may be more action in the north, particularly behind Dominica and Martinique. And we can also look at this in profile view. And again, we have evidence for a pretty strong lithosphere in the north in B and C, but then by the time we get down to Grenada, that lithosphere-asthenosphere boundary isn't as visible. Okay. And then we can also look at where the S to P receiver functions are visible in terms of just in map view. So again, showing you that in the north, we may be seeing some of the incoming plate lithosphere-asthenosphere boundary and also some beneath the arc, but also what I've plotted here is a 4.3 kilometer per second contour from the surface wave shear velocity model. And it basically draws a ring around where that lithosphere-asthenosphere boundary is visible in the back arc. So we're pretty confident that there is melt ponding in the back arc from both receiver function imaging and from surface wave imaging. So again, what this is setting up is that, okay, well, fluids and fluid pathways and melt pathways in subduction zones may be more complicated. And again, this is just another piece of evidence. We also performed ambient noise imaging in the region. And again, I'll just focus on the right-hand side for these different profiles. So the top profile here is going along the Greater Antilles arc, so Puerto Rico, the Virgin Islands, and the Mona Passage, and it looks like Mona Passage, and just beneath Virgin Islands might be a little bit of a rift zone, and there's a low velocity anomaly that might be associated with the rifting there. And then just looking at the profiles going and A to A prime, B to B prime, and C to C prime is a long arc. But what we can see in the long arc profile is, again, we have a low velocity anomaly beneath Dominica and Martinique, just below the Moho, which we would interpret at around 20 to 30 kilometers depth. So again, suggesting that we have a heterogeneity in where our mantle melt anomalies, and again, suggesting maybe 3D flow or heterogeneity is an important part of the story. Okay, and then this is a nice study from George Cooper, and what we tried to do here was to integrate all of our observations. And so George measured uh, delta 11 boron, which is a geochemical proxy for where uh, fluids in the melts in the magmas may have come from, and it's kind of color coded here. So this yellowy color is indicative of fluids that would come from sediment. The bluish color is indicative of fluids that would have come from oceanic crust, and then the greenish colors are indicative of fluids that would have come from serpentinized mantle material. And so the greatest anomaly in terms of serpentinized mantle prototype, serpentinized mantle prototype source comes beneath Dominica and Guadeloupe, which is where our predicted fracture zone locations are. So there does seem to be a consistent story here from what I showed you earlier with the slab VP-VS anomalies of where fluids might be coming from deeper sources along the fracture zone, and the geochemical anomalies that suggest there is mantle, serpentinized mantle peridotite in those regions. It is pretty consistent. However, if we look at other evidence for fluids and melt in the region, our greatest anomalies are actually beneath. So if the B values, high B values would be consistent with large amounts of fluid release, which would be representative of, which is would cause more small earthquakes, which would give you higher B values. Um, and so, the largest B value anomaly is actually kind of beneath Martinique and Dominica. And this is also consistent with where the greatest low shear velocity anomalies are. And so even though the fracture zones do seem to have a signature and they do seem to be contributing fluids to the system, the greatest amount of fluids and melting seem to be coming from in between the fracture zones, which is again kind of consistent with what Jenny was showing is, oh, actually we can't really, the fracture zones aren't actually doing most of the work. It's probably chunks of heterogeneous serpentinized core complex material in between these fracture zones that's actually doing most of the work. The kind of negative consequence of this is that those are a little less predictable than the fracture zone. So it doesn't, we can't put our finger on a fracture zone and say, aha, that's where we're going to have the greatest amount of fluid release in the system. Actually, it may be more related to, the tectonics at the formation of the oceanic crust in the first place. But it is really cool that we can image this. The other kind of take home and kind of bringing it all together is that fluid pathways in the Lesser Antilles are not just straight vertical, that the cold hydrated channel being dragged down by the slab may be helping to move water and hydration further into the back arc, which may allow melting further into the back arc, which ponds beneath the base of the lithosphere and is then eventually guided back to the arc system. And this is kind of interesting and begs the question, is the Lesser Antilles unique in the global subduction zone system and that the fluid pathways are not vertical from where the fluids are released? Or is it just something special about the Lesser Antilles? It's a slower moving system and we're actually able to image it, whereas in other systems, the scope and scale of the subduction zone systems is different, and everything's just getting kind of smeared together.